So this is the organic paper the second organic paper we've done. The idea of a skeletal formula shows lines with vertices to represent bonds and carbons at the end of those lines. We don't draw the carbons, we don't draw hydrogens attached to those carbons. We do draw hydrogens that are attached to oxygen. So that's the correct structure for butanoic acid. But being 4 carbons, an like alkane, the an there, telling you there's no double bond to double bond to carbon, oic acid, carboxylic acid. So they're all representations of sort of butanoic acid. The only one that's skeletal is the top one. The second one, what's the structural formula for this compound? Well, this is again a skeletal formula. There would be an H here that's not drawn because it's on a carbon, so it's H, then C for that carbon, and the O and the O, and then the CH2, and then the CH3 at the end. So that one is C. If you take but1-ine, so but being 4 carbons, with a triple bond ine at the first carbon, so 1, 2, and then 3, 4. That's butine with a carbon there, 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 and there. If you react it with excess hydrogen, well, just like alkenes can react with hydrogen. They are reduced with hydrogen. First to the butene, but1-ene, and then the butene was subsequently reduced again, all the way down to the alkane if you add sufficient hydrogen. So we end up with butane. So B is the final answer there. Question 2. You all know this reaction. Actually, most of you do a pretty good effort at this mechanism. So nitric acid and sulfuric acid, you might remember, make the electrophile NO2+. The question though is, how is benzene reacting? Benzene is attacking that nitrogen, that positive nitrogen, and so the benzene is acting like a nucleophile there. It is donating a pair of electrons, pushing a pair of electrons towards the nitrogen. This is a question that was done relatively badly, I would say. Skeletal formula, skeletal, that's where people have gone wrong. They drew the structure correctly, but most of you, at least, that got it wrong, didn't draw proper skeletal structure. So pent for 5 carbons, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Pentan, no double bonds, and pentane, 2-ol, 1, 2. Draw an OH on there. You can write OH or OH without the line, but make sure your carbon is attached to the oxygen. And you've got to draw 5 chloro, 1, 2, 3, 4, 5. So on the 5th carbon we draw a chlorine. There's a bond first, remember, and then 2 methyl. So we need a methyl at carbon 2, 1, 2. So it's that. Lots of variations on that, which would be okay, but that's the answer. That was a repeat, so we didn't count it. This question, it was quite hard, I thought. Right, what's going on there is it's pretty hard to work out the oxidation number of carbons in alkanes, alkenes, alkynes, and various other things. But the way to go about it, and the way that I think it through, is I start with methane. I know that methane's got a carbon with 4 hydrogens. I know all the hydrogens are +1. So methane, all of the hydrogens +1, and the carbon therefore is -4. Right, overall it's got to be 0, hasn't it? If we then go up to ethane, we know that again the hydrogens are all +1, so the CH3s the carbon must be 3-, so that's +1, +1, +1. The same on the other side, so the carbons must be -3. So that's when you've got a methyl carbon. So in other words, when the CH3 is next to another carbon, then the carbon is -3, right? That isn't what the question was asking, but it gives you the sense of how to work it out. So if you've got the product, which is propane, this one would be -3, this middle carbon -2, the end carbon -3, because all the hydrogens are +1. And you can't just do 3 divided, the oxidation number of 3, 6, 8 divided by 3. I know some of you tried that, and that makes sense, the average one, but it did say in the question the second carbon specifically. The alkyne, the carbon at the end, the left hand side there, that was -3. That wasn't what the question was. This one's got 1 hydrogen on it, so this was -1. This carbon has no hydrogens on it, so this carbon was a oxidation number 0. So in the reactant, carbon is 0, in the product it's -2, and so it wants you to say here that this is a reduction. The carbon has decreased in oxidation number, and that happens of course when you add hydrogen. If you wrote hydrogenation, it was in the mark scheme as allowed. If you wrote addition, I allowed it because it is an addition reaction. I think question 8 was really hard. Wouldn't be at all surprised if many of you were caught out by this, but it was an example of a reaction you've seen. So you know if E plus was NO2 plus, then you'd know that it would form nitrobenzene and H plus. You're comfortable with that, you've seen that plenty of times, and you've drawn it later on in the paper. Bromobenzene would form in the same sort of a way, but instead of E plus or NO2 plus, it's Br plus, and that Br plus is made from, and you're not expected to know this, you're not being told this, but Br plus can be made from bromine and FeBr3. I'll show you how in a sec, but then it's just recognising this is an example of electrophilic substitution, where that's Br this time. Then you get H plus. Just as an aside, this is not covered by your course, but just to show you what's going on for interest, the FeBr3 reacts with Br2 to give FeBr4 minus plus Br plus, and it's that's the electrophile. Remember the benzene again is the nucleophile here. Phenyl ethanone, this stuff, eth and one ketone, ketone's got carbon either side of the carbonyl, so phenyl ethanone, 2 carbons, one ketone, can be made or is found in fruits, or you can make it from phenyl ethene. So ethene, 2 carbons with a phenyl group on it. You need to recognise phenyl, you need to know what phenyl is, and it asks you what the compound X is. Now many of you drew that as some sort of cation intermediate or whatever, but it doesn't mean that. It means something you can make from that you could subsequently turn into that in 2 steps. So water and sulfuric acid, really it's steam, isn't it? We know you have to do that, and so you should know that you go from an alkene plus water, steam and sulfuric acid gives you an alcohol, right? We've done that plenty. And you also should know that alcohols can be oxidized, and possibly you might know that it's potassium dichromate and sulfuric acid, though you don't need to know the oxidizing agent to get that bit there. So X, the X that you need, the alcohol that you need to make this ketone is with the OH in the second position in that carbon there, and that stuff can be oxidized to form this ketone. Secondary alcohols, remember, can be oxidized to ketones. So that was the answer to the question, what is X? And then you had to answer, if I just draw it again here just to show you, some of you drew it without the carbon making 4 bonds. It looked really slightly disappointing. But that's the intermediate compound. The reason it can form stereoisomerism, a stereoisomerism can either be cis trans or optical, and you have to say which one it was. So it can form optical isomers because it's got a chiral carbon. That there is a chiral carbon, and it's a chiral carbon because it's got 4 different things hanging off it. So I wanted you to say it has a chiral carbon. You should be comfortable and easy recognising that. Some of you talked about the fact it has 2 enantiomers, which might have been worth the mark, but I didn't give it to you. What type of reagent is required to do the second stage? The type of reagent is an oxidising agent because you're going from a secondary alcohol, as I just showed you, to a ketone. So I was hoping you'd say oxidising agent. It didn't ask you, in fact I changed the question to not ask you what reagent you used, because it's not in your syllabus. You're not required to know the name of the reactant now. Some of you wrote down potassium dichromate in sulfuric acid, but it's not what it asked you. It asked you for the type of reaction, which is why I wrote those 2 words into the paper and I put them in bold, so I want you to say oxidising agent. What's the compound? This was quite a hard question. Well done for those who got it. There'll be a minor product in this 2-stage synthesis, right? So we started off, remember, from phenyl ethene, and we've made, or most of you realised, or some of you realised, we must form this secondary alcohol to go on to make the ketone in the second step. But this is what we call Markovnikov addition, or addition of water to an unsymmetrical alkene, which means you can get the primary alcohol forming instead of the secondary alcohol as the minor product. So this is minor, major. But it specifically says, if you read back the reaction conditions, it says you've got an excess of the two stages. Well, it tells you you've got a two-stage synthesis. It tells you it includes the oxidation. So if you oxidize the primary alcohol, you'll either have the aldehyde, which is that, or more likely, really, you're going to end up with the carboxylic acid, like so. Okay, quite a hard question. You have to spot really that this is addition of water to an unsymmetrical alkene. Again, remind you, you're not expected to know the conditions to do nitration. I have shown you them in case it comes up for familiarity and you end up making NO2+. And some of you had a go in the lesson at drawing the Lewis structure of NO2+, which is that. So that's what's attacked there. The answer to that question I was looking for was NO2+, the electrophile which benzene, or in fact the substituted benzene, attacks, right? Interesting, some of you put all sorts of things here, like H+ and various other things, but then you drew... Jill, can you close the door? I've literally no idea if I paused it at the right place there or not. If I've been waffling ages and not talking to you, that's the mechanism up to this point. 1 mark. 2 marks for that drawn correctly. The position of that semicircle, the open bit pointing to the the carbon that's substituted 4 times there. The 3rd mark is the breaking of that bond, replacing the 2 electrons that we use in step 1. And then finally, the correct product, the NO2 there, and H+, needed the H+ remark. What are nucleophiles most likely to react with? So a nucleophile classic example would be SN2. The 2 is for nucleophile, right? So the SN2 mechanism that I've shown you is hydroxide attacking halogenoalkanes. So that's your answer. You're pretty good though, for question 11, at drawing the energy profile for SM1. SM1 is 2-step. You've got the intermediate. It looks something like that. So most of you got that question right, which was over the page up here. So that was done well. Largely. Again, if you revised at all, you were getting that right, I would say. Most of you. Right. Funny old question, because it's asking you about something you've never heard of or seen before. So organomagnesium compounds. So that's organomagnesium. Organo because it's an organic molecule with a magnesium strapped in there somehow. And you're not told much about them. You don't need to know much about them to do this question. But you're told the overall equation. So you can see that in the end, hopefully, that CH3 ends up as one of these CH3s. Let's say that one. Doesn't matter which one. Right, or you can make this stuff from taking an alkene and reacting with water. If you take an alkene and react it with water, you add water across a double bond. Right, so let's work out what that would be. So state the name. Okay, we've got to state the name of compound B to start with. So this is 1, 2, 3 carbons as a longest chain. So let's start off by writing propane. But it's not propane, is it? Because it's got an OH on it. So it's propan 2-ol, because it's on the second carbon. 1, 2, 3. So propan 2-ol. But it's also got a methyl group on the second carbon. So it's 2-methyl propan 2-ol. 2-methyl because it's on the second carbon. And that's an example of a tertiary alcohol there. Part II was asking you about asking component A and component B at liquids at room temperature. What's the strongest intermolecular force in compound A? Let's put compound A again. Compound A cannot make hydrogen bonds because it's got no OH or NH or FH, but it does have a polar bond, delta plus, delta minus, which is a permanent dipole in that molecule because the molecule is not fully symmetrical. So it's got a dipole going through it like that, and so it makes dipole-dipole interactions. Lots of you got the sigma pi things wrong. I think because you forgot the hydrogens. If I draw it in full, you'll see that there are lots of more sigma bonds than perhaps you realised. So 1, 2, 3, 4, 5, 6, 7, 8, and one of these is a sigma bond, so it's 9 sigma bonds, and then the C double bond O has got a pi bond as well, so 9 and 1 there. The hybridization of the central carbon was marvellous. Everybody was able to say more or less that it was sp2, so pretty good there. And then an isomer of that stuff that exists as optical isomers, right? So we've got to have a chiral center in a molecule with 1, 2, 3, 4 carbons. H9OH. Is it 9? 1, 2, 3, 4? Yes, H9OH. The only possible, if you just sit and scribble some isomers down of C4H9OH, you will end up soon enough with CH3, COH, H, CH2. So it's just a secondary alcohol. So this is butan-2-ol, and it's got a chiral center because the carbon there with 4 different groups coming off it. And then we have to work out what the alkene was that was required to make that. Now, to make an alcohol from an alkene, you're adding across a double bond. So you almost need to think backwards here. So we've got that OH is being added to it, so the double bond must start here, so it must end up going to any one of these carbons, let's say this one. And that water was an OH, and it was one of the hydrogens on here. So that's the water that was added across. So let's try draw that alkene. There's the C to double bond C. The 2 hydrogens that are left will be on there. And this carbon here is the one I've just drawn here. And then we've got to draw a CH3 and a CH3 coming off it. I can understand why people find that hard, and lots of people could find that hard, but some of you did well to get that. If you take that molecule, which I've drawn skeletally here, and add steam to it, you'll get 2 products. It's just like the question earlier on. So you'll get either the Markovnikov addition, where the hydrogen mostly adds to the carbon with the most hydrogens on, where you get that, and the hydrogen from the water ends up on this carbon because it's got the most hydrogens, but you could also get the OH at the other end, which is that molecule. So this is the major product here, and it tells you that in the question anyway. So this was poorly answered and needs revising and needs working on. We've done it many times in class. You have to know that it's not anything to do with the stability of the product. You all are able to draw the mechanism, and yes, this is the water mechanism, so it's one we've only learnt recently, but it's the same as all of the other mechanisms really. So let's just go through that. The double bond attacks the positive H plus from the acid that's in there, and we end up with 2 possible carbocations. Carbocation with the plus in the middle, which is a tertiary carbocation, or we've got a carbocation at the end of the molecule, which is actually a primary carbocation. Some of your answers I might change it to secondary because I didn't think about it hard enough. And it's the stability of the carbocation that matters. And you have to say that the tertiary carbocation, or the carbocation in this position, is more stable than the carbocation at the end, or primary carbocation. And then you'd explain that by saying, because it's surrounded by 3 electron releasing alkyl groups that exert a positive inductive effect. And that was moderately well answered by many of you. If you take the alkene though, make a polymer, just like any polymer, addition polymer anyway, what you do is you draw the 2 carbon unit. Doesn't matter whether it's polyethene, polypropene, poly 2-methylpropene, it's always a 2 carbon unit overhanging bonds. Always, always, always. This carbon is this carbon, and hanging off that carbon are 2 hydrogens, so we draw those 2 hydrogens. This carbon here is this carbon here, and hanging off that carbon is a CH3 up the top and a CH3 down below, and that really should be joined to the carbon there. You got the mark if you didn't do the N, but let's get into the habit of drawing the N. I'm going to pause the video and charge my computer up. This mechanism, you should be pretty good at this. So the first step, in fact, right, yeah, first step, you know, is BR2 splitting. I'm not even going to write it out. Whoops, to give 2 BR dots. That's the initiation step. The propagation step, which is what we're doing here, we take one of those BR dots, react it with ethene, CH3, CH3, and that ends up with HBr and CH3, CH2 dot. You've got to know that mechanism, just no getting around it, and that would have led you to that answer. So if you weren't getting that answer, it means you don't know that mechanism well enough yet. But bromine also can react with molecules in the dark. It doesn't react with alkanes in the dark. Bromine water, as you know, as you have known since year 10, bromine water reacts with alkenes and does it whether it's dark or light. You don't need the UV. So you have to look for which one of these is an alkene. Bromine water reacts with alkenes. The only alkene here is hex-1-ene. Lots of you put all sorts of strange answers. It's just the bromine water test. Xylene is a derivative of benzene. It's a benzene with 2 methyl groups hanging off it. So instead of hydrogens in this position, we've got a CH3. Remember benzene, I think some people are getting confused about benzene. Benzene is C6H6, so on each carbon there's a hydrogen. With xylene, 2 of these are replaced with CH3s. Now, bromine does react with alkanes. We know that. We've just talked about that. It reacts with alkanes in the presence of UV light. But that comes later on. Question A is saying state the number of H-NMR signals for this isomer of xylene and the ratio. Right, this was done, I think, relatively poorly, so I'll spend a moment on this. The first thing I would do, unless I was really confident, is I'd draw all the hydrogens on the molecule, and nothing's stopping you doing that. No examiner is going to tell you off for drawing hydrogens, and those people who didn't draw the hydrogens or drew some that aren't there are struggling. So there's a hydrogen on 4 of the positions, and then you've got the CH3s. Now this is a symmetrical molecule, which is where some of you got unstuck, I think. So this CH3 here is equivalent to this CH3 here. So we'll call that type A hydrogens. This hydrogen is the same as this hydrogen, right? But if these are equivalent, these must be equivalent as well. So all of these, all 4 of these are equivalent to each other. So B, 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 and B. So there's 2 signals. So there's 2 hydrogen environments. Relatively difficult example because you have to spot the symmetry in the molecule. And the ratio is 6:4 or 3:2, depending on whether you like to simplify your ratios or not. It's then asking you to draw an isomer of xylene. So same structure, same molecular formula, but different structure, but it retains the benzene ring. So it's a benzene ring on it, and there are a couple of possibilities. Either you've got, and by the way, some of you drew benzene without the circle. That's going to lose a mark. So you could either have them opposite each other, CH3s like up there, or you could have one here and one here, which lots of you drew, or you can have a CH3 like one there and one there. We call this one para when they're opposite, ortho when they're next to each other, and meta when they're like that. You don't need to know that, just telling you, don't know why. Or you could have, instead of 2 methyls, you can actually have CH2, CH3. So this has still got the same number of hydrogens, believe it or not, although there's only 1, 2, 3, 4, 5 hydrogens on the chain here, we've got one extra hydrogen now on the ring. So there, any of those would have done. The initiation step of bromine reacting with alkanes, most of you got right. And I was hoping that you were going to do this, showing that homolytic fission reaction to Br dot. Look how often it comes up. It's come up on all three of the papers we've done. Organic chemistry. The clue here is that dimethylbenzene, which I'm going to draw again, behaves like a substituted alkane. In other words, how the alkanes react. In other words, it doesn't react through the benzene, or in this case at least. And it's just asked us a question about free radical formation. Right, so it's going to be a free radical formation. This is a CH3. It's going to behave like an alkane that substitutes, behave like methane or ethane or methyl ethane before methyl ethane or methyl propane or something, some sort of substituted alkane, some sort of alkane type thing. In other words, it does a free radical substitution of an alkyl CH. So an H is replaced with a bromine. So any one of these H's, I'm going to choose one here, is replaced with a bromine. But it says there's two products. We've lost an H from here, we've lost a Br from here, so we're left with HBr. You know that mechanism, you've written out that mechanism dozens of times in class and presumably at home as well. But can you apply it to a slightly weird example here? If you take a carboxylic acid, I'm going to draw this fully, and some of you might need to do this to see what's going on, and you react it with an alcohol, and I usually point the functional groups to each other so I can see what's going on. So it's that secondary alcohol. If you take a carboxylic acid and alcohol, you get an ester, right? So that and that fall off, you get water as a byproduct, and you end up joining that carbon to this oxygen. So I would draw that here, so I'm going to draw it now. This is how I would tackle this question. I wouldn't even look at the answer till I knew what the answer was. And that's the answer, it's that ester, whoops, CH3. Okay, so then I look to see which one of these matches up. So CH3, C, O, O, CH, no, it ain't that one. CH3, COO, CH, CH3 twice. Well, that looks like the right answer. Just check the others. That's nothing to do with it. That's nothing to do with it. It's got the wrong length chain. So B is the right answer. Again, I'd really highlight here that addition polymerization of alkenes come up a few times, and some of you are struggling with this. Propene, when we're doing polymerization, we should think of propene like that. So the repeating structure is always, as I said before, 2 carbon unit with each carbon being the 2 that were the carbons on the double bond. Draw it all again without the double bond, put a little N there, and hang 4 things, 2 things off each carbon, 4 things in total, a CH3, an H, an H, an H. So if you drew that over and over and over again, it would be one of the carbons has got an H and a CH3, more of the carbons has got 2 H's, and that's A. And the last one, trick here, just draw the lines on there. Just do that and stick a double bond in there, and that's your monomer, that's your repeating, that's the monomer that's repeated. And that is the first one, isn't it? So CHCl, you'd have a double bond there in the monomer, CH3, job done. Right. Finally, we'll do the back page. This is done pretty well. Borrowing someone, we'll use this one because it's all right. And so the 2 functional groups on that molecule, you've got the carboxyl, which is the thing that you see in carboxylic acids, is one of them. The carboxyl group, and the NH2 there is an amine, or we probably should say amino for the IB because they like that sort of thing. Question B, 4BI, people did incredibly well actually. People found this really I was really pleased with how this was done. Most of you got something pretty close to the answer. And you drew an amide, most of you in the middle, and labelled it as an amide, which is good. Some of you called it a peptide. Peptides really only are amides that you form between amino acids to make polypeptides and proteins. They are amides, but we call them peptides in biology, not chemistry really. Some of you got caught out because you tried to draw the polymer, so you crossed out, you got rid of the OH at one end and the H at the other. That was a perfect answer for the polymer, but it simply asks you to draw the product when two molecules combine with one another. So some of you fell for that little bit, a little question there. When you've got amines and carboxylic acids reacting together, you get water as a byproduct, which makes them condensation polymers. And that's it. I hope that was all right.